Hello. So today I'm going to just do a fairly small talk on something relating to cognitive science primarily, but it's going to be cognitive and computational minds and kind of viewing that through the lens of cognition as a hidden and integrative process. So I like to frame it as cognitive function is based on neural learning. So when we commit to a cognitive task, we are essentially activating chains of neurons that have encoded or learned some stimuli. So think about your own learning. When you encode information, you retain it for a while, you then retrieve it for use within your working memory to solve a problem. Every trace of a memory that you have is within your brain, and those memory traces can strengthen over time as you're exposed to that knowledge. So activating a neuron is essentially just using that chain of neurons or that part of the brain for whatever cognitive task is required or requires that activation. So, we have approximately 86 billion neurons at our disposal in the brain, which seems like a lot on the surface, and it really is. But when you consider the additional connections between those neurons, you see how much more complicated it gets. So that's kind of just an initial framing. So each neuron can have many connections, and that can yield trillions of connections between neurons. So you'll kind of see why this idea of machine learning, machine cognition, if you want to describe it that way, isn't really comparable in the same way in terms of just the innate complexity. So, our neuroplastic tendencies can change or modify existing connections of neurons. It's one of the most foundational things to consider for our own cognition, that our thinking and our experiences and our exposure to stimuli can, create new connections between neurons. So learning is an adaptive and dynamic process. So how we learn and think with our human cognition and how we learn is kind of framed through sort of natural and biological learning. Machine learning isn't really the same thing in that framing. So as we activate those chains of neurons for those cognitive tasks or whatever was required, they can become potentiated or strengthened over time, or they can weaken over time. And that's framed through LTP, long-term potentiation, and LTD, long-term depression, respectively. And those two terms kind of, together define a lot of learning and memory processes, if you want to be simplistic about it. So, and my camera's blocking the words here again. It's a bit of a problem. So how neurons and the brain encode and process information is a baseline of inspiration for machine learning and AI. And we'll see why. But first, I'd like to consider a bit more of a biological basis of cognition and behavior as well, but the focus here is more so cognition. But activation thresholds. So neurons communicate electrochemically, electrically along the axon body, chemically at the synapse. The action potentials initiate these communication events, and they're all or nothing occurrences. So you can't exactly have a neuron that's partially activated. It is either there's going to be an excitation or an inhibition, or that means that a signal will propagate or it will not propagate. So it's helpful to view it as this kind of all-in event. Though you can certainly think about maybe the probability of these kinds of events occurring maybe that isn't as clear cut, but the events themselves are all or nothing. So an important concept is considering the threshold at which a neuron activates. So negative 70 millivolts is the resting potential, kind of just a normal resting state, and negative 55 to 50-ish is considered the activation threshold, where an action potential is beginning its initiation. So neurons can be inhibited in this Hauser communication. Some events can lead to the excitation of neurons, and in some cases you want neurons to be inhibited in some way. If you think about maybe visual processing, there can be sort of orientations of light that can excite certain neurons within the visual stream and inhibit other neurons. You don't necessarily want all of your neurons excited all at the same time. That wouldn't be pleasant. And, a sort of extreme excitation of neurons just across the entire brain could be implicit of something like seizure activity even. So not pleasant to think about having all of your neurons just excited all the time. The balancing process of excitation and inhibition is a really important dynamic. So bringing us into this framework of machine learning and trying to merge it into that framework of neural networks machine learning, we think of weights and biases, and I guess a kind of analogous comparison between them and the whole idea of activation thresholds. So weights kind of regulate the strength of the connections between the inputs and the neurons, the quote-unquote neurons, these artificial neurons, to determine how much influence each input has on the output. Keep in mind, again, with the machine learning, the neurons are artificial, and in concept, they're based on biological neurons, though we'll kind of see why machine learning models don't necessarily perfectly replicate neural behavior. So biases, they shift activation functions, and it can be something like a ReLU function, which is nonlinear and is good for complex patterns, or whatever function you like to use. Depends on the problem. Activation functions, following weights and biases, a result can be filtered, through activation functions to determine when an activation occurs. So I kind of consider that to be the equivalent of an action potential, even though it's not the same thing. It's sort of when this artificial neuron turns on or accepts input or passes a certain information along. It's just things are mediated or moderated by some other ongoing process, such as with an activation function. So machine learning activations, as I've said, are kind of maybe a reductionist way of looking at neural activity biologically, because despite the inspiration, there's not a lot of biological plausibility in this kind of framework. There are models of neurons that offer more biological plausibility, but these are kind of just, I consider to be kind of a utilitarian abstraction of the concept almost. So some miscellaneous insight to consider. Neurons can of course receive input from multiple sources due to the dendritic connections between them. So it can relate to what other neurons are doing, or whether or not a signal that's been propagated is going to continue propagation through excitation, or is going to be inhibited in some way. But machine learning models can be scaled to capture some of that innate complexity. As you see, here on the bottom left visual, you see an input layer and a hidden layer, which I'm going to reference in a bit later, because this idea of kind of intermediate hidden processing is very important. And then you have an output layer. The middle layer is They're also known as perceptrons. Um, so they kind of are intermediaries in a way of what the input is providing, such that the output is accounting for all these kinds of intermediate processing and biases and whatnot. So, and to the right, we kind of just have an action potential graphic with voltage and time. So, you have your resting potential, your activation threshold potential, depolarization, which is kind of the initial stage of an action potential. And then you see the peak, and the repolarization brings us back to a resting potential. And then the hyperpolarization sort of happens on the opposite end, and then we were brought back up to resting. So this kind of pattern is really typical of action potentials, this spiking pattern. And there are different ways of kind of replicating or modeling that. Some manifestations of it are more simple, like treating an action potential as just a point on a graph that it happened, but you don't really capture any other nuance other than that it happened. So there's quite a bit that you can do with that. So this is kind of more so from an external source, but it's relevant to know. This is from IBM. But training on data can actually be too efficient, and you might think that's a strange concept. How can you be too efficient at something? Well, with this function on the left side, it is relating to back propagation, which is kind of to tune parameters so that they get closer to correct answers. The idea that I have highlighted myself is that the data or the network converges to a configuration of weights and biases that tries to mitigate error or minimize it. So some models can be very complicated and have millions or billions of parameters to consider. So these more sophisticated models can become very efficient at predicting data, but this can also lead to overfitting. So this is when networks are dealing with data that is familiar to another data set they've already been thoroughly trained on. And data that is overfit can actually have a reduction in accuracy when it's applied to a different data context. So to the right is some formulation. You might see sigma pretty commonly in statistics as kind of a summation function. So you kind of have, your weights, your biases, the weighted sum, which is a linear transformation, and then the activation function, such as a ReLU function, as being nonlinear. So you are kind of summing up a lot of inputs such that the output would have perhaps ideally a high degree of accuracy. But again, if that accuracy is too high to the point that you become too efficient at predicting data, you can overfit and begin to predict something that actually is accurate in one context but not accurate in another context. So this is kind of more of a maybe social, cognitive, even philosophical framing of this dynamic. Not so much of machine learning, but the dynamic of human cognition and machine learning. What makes our cognitive abilities special? Well, our minds are better at learning from fewer examples. We don't need, millions of data points to come to predictive conclusions about things. And we naturally kind of reconfigure our learning and memory passively and actively. Think of neuroplasticity, a really foundational concept in psychology and neuroscience for learning and memory, and just what makes the brain as dynamic as it is really foundationally rooted in neuroplasticity. So The brain is generally better at integrating a lot of simultaneous information for some ill-posed problems at times, like visual processing. And computer vision is not a very simple task. So, computers are better at serial processing in the sense of, maybe some kind of quantitative thing, like a series of mathematical logical occurrences that has a very definitive predefined outcome. But if an outcome maybe isn't predefined or is very dynamic or integrative or can change constantly, maybe you need to have the more dynamic processing that the brain generally makes use of. So we can acknowledge and mitigate our own bias. I'm kind of trying to draw an analogy between them, like biases and weight and our own cognitive bias. But a machine will still be trained on data bias from humans themselves. So, of course, if we're biased and we train something, it's going to take on those biases as well. Um, so I don't really think that cognitive bias is removable totally. By any stretch, I don't think so. But I do think we have to accept some possible degree of bias or error within our thinking or data on some level. To think that error or bias can be totally eradicated, I think is a little bit naive. So this is a really foundational, conceptual, kind of philosophical question again. When thinking about the mind, because behavior is so complicated and memory is complicated and humanity is complicated, there's a lot of analogous comparisons that are often made that aren't as concrete as one would like. But that's because our understanding of the mind and the brain is still, I think, in an elementary stage. We don't fully understand the brain, to say the least. So what is it to really think? Well, a machine is not really thinking per se. It's just combing through information that it was given. Input, code, a command, what have you. Of course, we also process inputs, but our cognition is more emergent, sort of out of all the activity of neurons, their collective activity between those trillions of connections that I mentioned before, you have kind of emergent properties that are not solely defined on the basis of a single neuron, but on the collection of many things happening all at once. So with awareness or having a mind at all, human cognition is kind of evidence of that. So how those emergent processes come along in a cognitive context is the crux of cognitive science and cognitive neuroscience. And this can be explored through computational means like computational computational neuroscience, I mean to say, and ways of modeling that neural behavior in some complex ways, most of which I do not understand, unfortunately. So I like to think of a black box model. This is kind of a way of viewing, I guess, the processing and retrieval of data or some input or output condition as being very just simplified, as in you give an input, you get an output. Behaviorally and cognitively, that doesn't really sufficiently describe human cognition. If you go back to the outdated framework of behaviorism, you might have kind of seen this mindset adopted of just you give someone an environment, a stimulus, and they behave a certain way, and that's it. It's kind of a primitive framework, really. But for the sake of computation, it largely works well enough. Most of us, in a general sense, when it comes to computational matters, only really care about an input and an output, what the results are, what is being produced. That's kind of what we strive for anyway. But with our own cognition, intermediate, or this kind of hidden intermediate processing that we also see reflected in sort of the hidden layers of these machine learning models is a very important thing to factor in. So I do apologize for this randomly coming up, but it's relevant. This is our code that I did. It's not efficient. I don't even think it's totally correct. The goal was just to import a package relating to a neural network in R. Now, Python, I think, is better from any kind of machine learning experimentation than R. R is mainly used for data analysis and statistics. You can do machine learning in it. I just don't know if it's intuitive, but I did it anyway. And there's probably riddled with errors, so. But starting from the left, top leftmost image, you read your data files into R from whatever the name of the file is. And then, you kind of define some parameters. For example, this data set I imported was from diabetes risk assessment, but some of the data was categorical, meaning that it isn't defined as an integer or a number. It's just like a yes, no. It's binary. So you would kind of turn a yes response into a 1, a no response into a 0, or if it's kind of, I guess, nominal, if you want to be more specific about that kind of data. Nominal data is just categorical. So if you're going to transform it into a number, it's usually going to be binary, such as, male option is 1, female is 0. So that's kind of what that is. So you kind of define your data sets as to what you want them to be. And you set a seed. I don't know why I chose 1. I don't believe that's the proper number to set for a seed. But what seeds do is they promote stability within a program. So that if there's like random number generation or a sequence of numbers being ran, a seed instills stability so that numbers don't go haywire, apparently. I'm not sure of the technicalities of it. So you kind of have a training and testing set for your data. Again, I don't know what this looks like in Python. I do not use Python for this, but I want to because it's probably better. On the right side here, the important thing to notice is more or less this hidden layer I have set to 3 here. And I wanted to kind of test how changing the hidden layers would affect the accuracy. And of course here I also think with linear output being set to false, I believe that is due to it being based on a ReLU function or a nonlinear transformation. So having it set to false in that context makes sense, and I hope that is correct. So again, with accuracy, we're going to go down to the very bottom image here. The accuracy that it reports is 97.12%, which is good. I'm assuming this data set is perhaps easy to predict from because maybe the risk assessment is well defined here. But, with risk assessment for disease, it can be quite complicated. Maybe because this is just diabetes, the outcome is a high accuracy. But if it were sort of maybe conditions that had a comorbidity and you were trying to assess many different conditions all at once, it might be a bit harder to set this up correctly. So, but what if we change the hidden layers? Here I have it set to 5 instead of 3, and the accuracy goes down to 95.19%. I'm not sure if that indicates that this was done correctly. Again, I give that disclaimer, but it shows that you can have sort of your biases, your weights, your hidden layers. You configure them in a certain way to get an outcome, the most accurate outcome. So some changes can increase accuracy or reduce accuracy. You would kind of fine tune your parameters to get the outcome you want. But of course with here, you can plot. This comes with sort of a natural display of a neural network. if you plot it, so before I get to the image on the right, which is very messy, I'll go to the image on the very bottom. That's kind of your, this is kind of your data environment in R, and it just kind of shows the active data being read into the program. The number of observations and variables and the other things you've parameterized, uh, whichever. So here you can actually see that accuracy reported here, the 95% accuracy. It's not reflecting the other accuracy of 97% because I overrid it. It was overwritten with this other value. But on the right, you have this graphic of a neural network that's produced by the plot that comes from this package. And it's very messy. It's illegible. I don't really like it at all. But it's just showing how all the weights and biases kind of converge to produce a prediction or an outcome. So all of these input layers are sort of converging towards a prediction or an outcome. And the weights of these inputs can determine some aspect of the output. But again, these numbers, you can't discern. They're merged together. They're laid on top of each other. I'm sure there's a better way to have this visualized, but I don't like it. So lastly, here is a visual of what happens to these kinds of machine learning models for underfitting and overfitting. So if you have a data set and your model isn't well trained to it, it can underfit, meaning that you get results that aren't really reflecting the nature of the data very well. And that means your model is kind of failing at what it's striving to do, which is unfortunate, but it happens a lot. But conversely, a model can become so efficient at processing a certain data set that it overfits, meaning that it so precisely predicts the outcome that when you try to expose that model to a similar data set, it can bias the results toward a specific outcome, even if it isn't actually accurate in that context. So you can not be accurate enough, or you can be too accurate. The goal is to be accurate, but not so accurate as to be biased towards that highly specific outcome. So I like to kind of reflect a little bit here that while a machine can be too perfect or overfit at predicting the nature of data, how about our own cognition or our brain? So this is kind of, again, more of an abstraction of these concepts, but we do adopt naturally a lot of pattern-seeking tendencies to confirm results or to find what fits, even if it's not applicable to the context. So think of cognitive bias that you would learn about in, say, cognitive psychology or cognitive science. Bias seems to be quite a foundational thing to consider within mental processing, data processing, research. It's something that has to be navigated. So the psychological basis of learning is an observation and experience creating permanent behavioral changes. So do you think it is better to only learn in the most efficient way? Does that always produce the best outcome? In our thinking or in other contexts, I'm interested as to what you would think about that. So thank you for listening to this little mini talk, and I hope to produce more soon. So goodbye.